Many of you must have wondered how the orbits of planets are computed and how it was done earlier and how it may be possible for us to do this in a relatively simple way. Okay. Uh, so understanding this involves some use of calculus. So this particular video is going to be really calculus heavy. Okay, but I'll try to minimize the use of mathematics here and give you some physical insights into the problem. Okay, as much as possible. Now, if you look at this diagram here, we have an ellipse. We have an ellipse like so, with one of the focal points at C and the other at D. And so we have a planet that's red in color, and it's moving in this elliptical orbit around the sun, okay, which is at center C. So come to think of it, there is really no reason for a planet to follow a purely circular orbit. Right? So the elliptical orbits can be thought of as more general cases of circular orbits. So when the ellipses become more and more regular shaped, they start looking more and more like a circle. So nevertheless, let's think of how we can look at this problem. So what we will first do is we'll try to find the equations of motion that are relevant to this problem, right? And then we will use some ideas from the conservation of energy, okay, starting with the conservation of energy to actually compute the orbit of the planet. Okay, so let's think about that. So here, if you look at the position of this planet, okay, it's located at a certain xy position. Okay, you can at a certain xy position, but because this involves uh, rotational motion, around a central point, so it is helpful to think of the rotation in polar coordinates. Eh, So we think of the rotation in terms of r and theta instead of uh, x and y. So here, the r here, okay, is the vector connecting the center with the location of the planet, and it equals r times a unit vector ur that is in the direction of r. Okay, there's a unit vector ur in the direction of r. So now, if you look at ur, okay, ur is essentially nothing but cosine theta times I hat plus sine theta times j hat, right? Where theta is the angle made with the x-axis here, and I is a unit vector along x, and j is a unit vector along y. So, and here is u theta, okay, that's a unit vector along the theta direction, right? And here u theta is perpendicular to ur, so you can write this as minus I minus, let's make it consistent, minus sine theta times I hat plus cosine theta times j hat. So if you were to take a dot product of these two vectors, so we get cosine theta times negative sine theta plus sine theta times cosine of theta, and that comes out to be 0. Okay, so let's go ahead and let us find the derivatives, right? The derivatives of ur and u theta with respect to theta. Okay, so because these will be useful for later on, right? So if you d do dur by d theta, you get minus sine theta times I hat plus cosine theta times j hat. Okay? And du theta divided by d theta equals minus cosine theta I hat plus, or rather minus sine theta of j hat. Okay, so we have that, and then we see that this is actually equals negative of u of r. Okay, so that's an interesting observation. Okay, so now let's leave this aside, right? And let's look at finding the velocity. Right? The velocity is nothing but the derivative of r with respect to time, right? dr with respect to time, okay? And it's in vectorial form. Okay, so now what we will do here is that we know that r is this, so we'll differentiate, okay, using the chain rule, right? So or we take the, the differentiation of the products, right? So here we have dr or dt u of r plus r times d u r divided by dt, right? So now d u r divided by dt equals d u r divided by d theta and d theta or dt by the chain rule, right? So, and d theta, okay, or dt is called theta dot, okay, and dur or d theta, okay, is nothing but uh, is nothing but u theta, okay, because if you look at this expression dur over d theta, it equals to minus sine theta I hat plus cosine theta of j hat. That's exactly the same thing as this, okay, and so we write this as u theta. Okay, so there we have it. So now, so the velocity expression can be written here as r dot. Okay, we write dr or dt as r dot, right? That makes the expression a lot more compact. ur times u hat of r plus, okay, r theta dot u theta. Okay, so that is the velocity, you know, in polar coordinates. So now let's find the acceleration in polar coordinates. So this is now dv over dt, okay, okay, equals, again differentiating using the product rule, we get this plus r dot du r divided by dt, okay, plus r dot theta dot u theta plus r theta double dot u theta plus r theta dot du theta or dt. Okay, so that's what we get here. Now let's reduce this expression here for acceleration into a more simpler form. Okay, so let's do that. So let me write it like this. Okay. So here dv or dt, okay, equals r dot u hat of r, and dur or dt we already know to be theta dot u theta, so we plug that in here, plus r theta dot u theta, okay, plus r dot theta dot u theta, okay, plus r theta double dot u theta, and du theta or dt, okay, du theta or dt, okay, is nothing but du theta or d theta times d theta or dt, okay. So this is essentially, you can write this as du theta divided by d theta times d theta or dt, and this is nothing but negative u of r, and d theta or dt is theta dot, right? So you can write this as minus r theta dot or theta dot square times u hat of r, okay. So that's what we have. So let's collect the terms of in u hat of r and u hat of theta, so we get this, right? So we get r double dot, and this was not written properly, so I'll write that, r double dot minus r theta dot square u hat of r, right, plus 2 r dot theta dot plus r theta double dot u theta, right? So essentially this term and this term together gives you 2 times r dot theta dot, and we have this term r theta double dot, so that makes up the rest of this term, that's the coefficient of u theta, and we take this expression and this expression and club that together, okay. So here what we see here is that the acceleration vector here essentially has two components, okay, has two components. So in the r direction, this is r dot minus r theta dot square, and the acceleration in the theta direction is 2r dot theta dot plus r theta double dot, okay. So now one of the things we do know here is that there is no acceleration in the theta direction because the angular velocity does not change. So this we can set this to be 0, okay. And we also know that the a time angular velocity in the radial direction, so angular acceleration in the radius direction, when multiplied by a, okay, by m gives you the net force in the radial direction, right? And essentially, so we'll take out the vector signs because right now we are dealing with components, right? So this equals minus g, the mass of the sun times the mass of the planet divided by r squared, okay. So essentially we have this expression, okay, a of r, okay, equals minus g m by r square. So effectively we have this r double dot minus r theta dot square equals minus g m over r squared, okay. And that is the equation of motion, okay, for the planet around the sun, okay. So I hope that helps you to understand, how to proceed. Now obviously what we can do here, okay, we can try to integrate this equation, and find r as a function of theta. Okay, we can try to do that, but it ends up being a lot more complicated, and I'll show you a simpler method of doing this. Okay, a much simpler method of doing this. Okay, so here there we go. So one of the things to understand here is that the the energy of the system is constant. Okay, and not only that, the angular momentum is also constant. And why? Because there are no external forces here. Okay, so in the planet and and the sun system, there are no external forces, so the energy is conserved, right? Also, the angular momentum is conserved, right? So essentially, the energy can be written here as the sum of the kinetic energy and the potential energy, right? And the kinetic energy has two components, right? Uh, it has a component from linear velocity, that's half mv square, and it has a component from the angular velocity. Okay, so that's the rotational component, and that is half times I times omega square. Okay, so and the potential energy of the system is nothing but minus g capital M little m divided by r. Okay, so we can add these two up, right, and make that equal to the total energy of the system, which is constant. Okay, so now uh, before we do that, okay, so we must understand that the in rough terms, we can write the angular momentum, okay, equals I times omega, okay, and it is equal to m times r square times omega. Okay, and the kinetic energy of due to rotational motion, okay, equals half I omega square. Okay, it's half I omega square. Okay, so now half I omega square, so what we can do is that um, we can write omega as L divided by mr square, right? Okay, so essentially uh, we have omega equals L divided by mr square. Okay, so and that is nothing but theta dot, right? So that's nothing but theta dot. Okay, so let's do this. Okay, so let's plug everything in here. So we get half mv square plus half mr square, okay, theta dot square, that's omega square, okay, minus g capital M little m divided by r equals to energy, right? So that's what it is, and theta dot is essentially L divided by mr squared. So we'll write this as half mr square L square divided by m squared r to the power 4 minus g capital M little m divided by r equals E, and here is half m, and v is nothing but r dot. Okay, so that's the expression that we're going to get. So now to simplify this further, we get half times m r dot square plus half the one of the m's cancels out, two of the r's cancel out, L square divided by m r square minus g capital M little m divided by r equals E. Okay, so that's what we have. So what we get here, okay, is we see that all these are independent of r dot, right? So what we can do is we can collect these terms on the right hand side, and we can write an expression for r dot very simply, okay, as r dot equals 2e over m, right, plus 2gm divided by r minus L square by m square r square, okay, and we take the square root of that, okay. So there is that. So now we know that uh, r dot. So let's try to convert this into an equation that involves theta instead of r dot, okay. So this is nothing but dr over dt, right? So what we can do here is we can write uh, d theta divided by dr equals d theta or dt divided by dr over dt, okay. This is nothing but omega divided by dr over dt, and this is omega is nothing but L by mr square, and divided by r dot, and r dot here is 2e divided by m plus 2gm divided by r minus L square divided by m square r square, and we take the square root of that, okay. So that's what we have. So let's see, so let's do this. Let's write d theta here, take this multiplication on both sides with respect to r. So we get L by mr square dr divided by 2e over m plus 2gm divided by r minus L square divided by m square r square, and we take the square root of that. And let me write this a little bit better, and that is gm, okay. And we integrate, okay, both the sides. Now here there is a little bit of a trick involved, okay. So what we do here is that we set u equals 1 over r squared, okay. So we get du equals, okay, or rather we set u equals r, okay, we don't set u equals r. So therefore du equals dr divided by r square with a negative sign up front, okay. So that's what happens, okay. So now when so we can just plug everything in here. So we have theta on the left, okay, is nothing but L divided by m, okay, and minus du, and here we have in the denominator 2e divided by m plus 2gm divided by r min, and instead of 1 over r we have u, okay, minus L square divided by m square, and we have u square here, and this is an easier integral to solve, okay. So now let's take this equation, and let's take the denominator here, and let's try to factorize that, okay. So what we do here, okay, is that we set this particular term here equal to b, okay. So we set this as b, this we call this as c, and there is no coefficient of u square, okay. So the denominator here, denominator can be trivially written as c plus bu minus u square. Okay. So if we take a look at this and we we factorize this, right? So to factorize this is very simple. So you can rewrite this as minus u square minus bu minus c, right? And so you can write this as minus u square minus bu plus b square divided by 4 minus c minus b square divided by 4. So essentially this becomes minus u minus b divided by 2 square minus c plus b square divided by 4. Okay, so that's what we have. Okay, and then I've not been dealing with the square roots yet. Okay. So this the whole thing becomes okay c plus b square divided by 4 minus u minus b divided by 2 square. Okay, so what we will do is we will plug this expression in the denominator. Okay, so we have theta equals minus du divided by c plus b square divided by 4 minus u minus b divided by 2 square, and we put this in the square root. So now what we do here is that we write this as alpha square, okay, and we write this as t square. Okay, so essentially, so t becomes u minus b divided by 2, which means that dt equals du, right? So theta can be written as minus dt divided by alpha square minus t square. We take the square root of that. Okay? And here alpha equals c plus b square divided by 4 with a square root on top. Right? And so we'll make the new transformation as t equals alpha cosine w, dt equals minus alpha sine w dw, and alpha square minus t square equals alpha square 1 minus cos square w equal to alpha sine w. Right? So essentially theta equals just alpha minus of minus alpha sine w dw divided by alpha sine w. So the sine w cancel out, the minus signs also cancel out. So this is just integral of dw. So just w. So for now we're omitting the integration constant. Okay. So now what we do here is that we substitute w for, equals cosine inverse t divided by alpha. Right? So essentially, so we get t divided by alpha equals cosine of theta. Okay, and we know that t here, okay, we know here as t here as u minus b divided by 2. So u minus b divided by 2, okay, divided by alpha equals cosine theta. So we can write this as u equals alpha cosine theta plus b divided by 2. Okay, and u equals 1 over r. Right, so that's what we have assumed a long time ago, right? So u equals 1 over r. So we have this here, 1 over r equals alpha cosine theta plus b divided by 2, or we have r equals 1 divided by v divided by 2 plus alpha cosine theta. Okay, so that is a very generic form for the uh, for the equation of the planetary orbit. Okay, around its sun. Okay, so that's the general equation. So let us recap this a little bit, because it has been a bit of a long proof. Okay, so for this particular purpose, um, we we know that the energy of the planetary system, uh, of the planet revolving around the sun, is constant. Its angular momentum is also constant because there are no external forces. You write the kinetic energy as a sum of the kinetic energy of translation plus the kinetic energy of rotation, and the potential energy here is the potential energy due to gravitation. So you add all these three terms and set that equal to E, right? So we know that the velocity is nothing but r dot, right? And the the omega is nothing but theta dot, right? And for the sake of argument, for simplicity's sake, let's assume that the angular momentum is simply the moment of inertia times the omega. So here it's mr squared times omega. So omega can be written as L divided by mr squared, and omega is theta dot. So we plug that value of omega in here, okay, to get this expression. Okay, we get this simplified expression, and we rewrite this expression in terms of the rate of change of the radius, right? But that's not it. So what we want to find is r as a function of theta. That's the whole idea. So which is what we want to do. So here, if you see, d theta over dr equals d theta over dt divided by dr by dt, and d theta over dt is omega, and omega here is nothing but L divided by mr squared, right? And then dr by dt is just this value, so we plug that in here. So we rewrite the expression for d theta as L divided by mr squared times dr divided by this expression in the square root that we had earlier, and we integrate both the sides, right? So here we make a transformation. So from here on out, it's just pure math, right? So we make this transformation as of u equal to 1 over r, right? And we get this equation, and we do some more mathematics in here to simplify it, right? So, and we end up with an equation like this. So we call this as C, we call this as B. Okay, so the equation can be this term in the denominator under the square root can be written as this, and it can be factorized this way. So we plug the factorized term back in here, right? And we take this and write this as alpha square, and we take this term and we write this as t squared, where t equals u minus b over 2 and dt equals du, right? So alpha is this quantity in, with a square root sign. So now we can write theta in a very simple way, and we use trigonometry to find the value of t equals alpha times cosine of w. We take the derivative, and this is what we get. In the denominator, this is what we get. We plug that in, and we find that theta is just an integral of dw. Okay, it's equal to w. We omit the the integration constant for now, because it's just going to be a multiple of 2 pi. Okay, so and we get something as cos inverse t over alpha. Okay, so we rearrange the terms here. So t over alpha equals cosine of theta, and t we rewrite t as u minus b over 2, right? Okay, and then find the value of u, and we rewrite u as 1 over r, and this is what we get. And this is essentially the equation of an ellipse. Okay, so we've gone through a fair amount of derivation to understand this. So we also understood how to find the acceleration in the radial direction, which is non-zero, and the acceleration in the angular direction, that is actually zero. Okay, so I hope this gives you a flavor for the mathematics behind something so complex. Okay, and it is very useful in the future for those individuals who want to pursue advanced physics, especially quantum mechanics. So anyhow, if you like this video, please click on the like button, and please subscribe so that you'll get more interesting videos in the future. Thank you.